Hi there, Chem Coach Powers here. We're about to have another physical science lecture about chemistry, specifically about chemical bonding. And this lecture, we're going to talk about the ionic, molecular, and metallic types of solids. And then we're going to talk about a network covalent solid. We're going to talk about how these different things have different melting points and why they have different melting points based upon their characteristic properties. We're going to talk about Lewis dot structures or electron dot structures or electron dot notations, a few different names for them. And you're going to see how to arrange the electrons around the atoms so that you can start to predict how atoms are going to combine together to form compounds and molecules. So let's go ahead and get started today. We're going to learn some cool stuff today. All right, so our objectives today are to differentiate between ionic, covalent, and metallic bonds. We're going to talk about the different types of elements that are involved in these, the way that they are dealing with their electrons with these different ones, their structure, okay, and then their properties, okay. Then we're going to draw models of these molecules using these electron dot or Lewis structures. Okay, so you guys are going to have fun doing this kind of stuff today. So let's talk first of all about our three basic types of solids and what makes them unique. The ionic compounds have metal-nonmetal combinations. So those are the elements that are on the left side of the periodic table combined with the elements on the right side of the periodic table. Okay, and so when you combine those two things together, you end up with an ionic compound. If you have nonmetals connecting with other nonmetals, you end up with what's called a covalent or a molecular compound, okay? And then if you have metals combining with other metals, then you end up having a metallic compound, okay, or a metallic bond. So these are different types of bonds, and these different types of bonds, we use those same words to describe the types of compounds, the types of material, okay, or solids. So we could say an ionic solid, an ionic compound, an ionic bond. Now, those are not the three same things, but ionic solids are made up of ionic compounds which have ionic bonds. You see what I'm saying? That's the way that we're correlating these. Covalent compounds, okay, or covalent solids are made up of covalent bonds, and they have covalent, I just said, they're made of nonmetals and they have covalent bonds. Let's try that again. Covalent solids are made up of covalent compounds which have covalent bonds between them. And then metallic solids are made up of metallic solids are made up of metallic compounds. Well, we can't really call them compounds in that case. So we won't say compounds for metallic. You do say that for covalent and ionic, but you don't really say that for metallic. So metallic solids are made up of metallic bonds. All right, let's keep going. Our valence electrons. What's the difference between our valence electrons in these types of situations? Well, our ionic compounds have valence electrons that are transferred or given from one element to the next. Our covalent compounds have elements that are shared between the two elements. And our metallic metallic solids have some unique sharing. It's still sharing. We call it mobile electrons. It's like this mobile sea of electrons where they share a lot of different electrons all together. Our structures of these three types of substances. We have our network of crystal lattice ions, okay? So when we talk about the structure of an ionic compound, we say that it ends up in a network solid. So this is what we're talking about. Here we've got sodium is the green, sodium is the silver, chlorine is the green. This is basically sodium chloride is what we could represent this with. And there are a network of bonds. These are all ionic bonds between every two elements that are next to each other. And you can see that in this case, you've got 6 different elements surrounding one particular one, right? If there is exactly the same type of ionic bond that is between all of them, okay? This attraction that's taking place here. This is called an ionic crystal lattice, okay? Crystal lattice of ions. And it's a network crystal, okay? Now, in covalent bonds, you have molecules. These things are held together by hydrogen bonds. So I've got 2 examples of this, okay? And in this case, we've got some water. And the covalent bonds are little green bonds that are in between the oxygens and the red oxygens and the white hydrogens. And so these green bonds are the covalent bonds. But the hydrogen bonds are holding together one water molecule to another water molecule. And so these can form crystals too. But the thing we want you to know is the molecules are distinct individual units. Each of these little water pieces is a distinct unit. Now this is all interconnected, and they're always interconnected. Whenever you get an ionic compound, all of the ionic components are interconnected in this way. The water could be different because it's a covalent compound. This little water could just be all by itself. Oh my goodness, I'm just destroying the water molecule. I lost the hydrogen. Okay, so that little water molecule could be all by itself. Now that is a covalent compound still, and it is a molecular compound. It's the same thing. We just have two different names for it. But it can also come into contact and bond with the other water molecules to form a crystal. Okay, so the crystal doesn't exist. Whoa, they've become attached. The crystal doesn't exist with each of the little pieces all by itself. They are always all connected together. But the covalent compound does have them each by themselves, and they can connect together, but when they connect together with hydrogen bonding, which is actually more of an attraction, and it's not a strong bond. And so they're a little bit different from each other. Here's another example. This is graphite, and so these are all made up of carbon atoms. And the carbon atoms are they are connected. You'll notice the white stuff is in between this time. The white ones are in between all of the green and black stuff, right? These are the hydrogen bonds in between. So hydrogen bonds are connecting the layers of the graphite, and graphite's the pencil lead that you guys have. And you're writing, when you're writing, your pencil lead is just shaving off one layer after another. This whole layer like pops off because the hydrogen bonding breaks, and you end up having just a whole bunch of little pieces of layers of graphite up on your paper. Okay, so that's what makes those things a little bit different. So your covalent molecules or your covalent compounds they do form crystals, but they're not crystals held together by the stronger bonds of the ions. They're held together by the weaker hydrogen bonds. And then we have metallic solids that are tightly packed together, right? Very dense. And they are also considered crystals. The solid form is also considered a crystal. But they're held together by this sea of electrons that we can talk about as well. But the idea here, and we'll show you a picture of it later, is that they are interconnected. They're not quite as strong as the connections here that we have with, the ionic compounds. But they are still strong, and they're stronger than the connections that we have with covalent compounds, okay? So metallic compounds are going to have higher melting points because of that. Oh, well, let's talk about our melting points. Here we are, right? So our melting points, ionic compounds very high, metallic compounds are high, covalent compounds are moderate. This is why we typically have solids, liquids, and gases, in the covalent compounds, but the ionic compounds and metallic compounds are going to be solids. Except for mercury. Mercury is unique, right? Very interesting exception, exceptee. And so you end up having these as being liquids and gases because the connections are not as strong, and so they melt a little bit easier. Okay, so you have moderate melting points. And then our electrical conductivity. Sorry, I've got a little sticky clicker here. Now, our conductivity of ionic compounds is good if it's melted or dissolved into water. But the ionic compounds don't conduct electricity by themselves if they're not dissolved or not melted. However, the metals do conduct electricity both in a solid or liquid form, and that's because of those sea of electrons, those mobile electrons that can easily pass electrons from one atom to the next, and that's what makes them great conductors. These guys need to have some free-flowing ions, and so in order to get them into that free-flowing state, you have to have this thing broken apart. And so when you dissolve this stuff in water, it actually comes apart really easily in water, right? You can just put some salt crystals in water. All of a sudden, each of these little things come apart, and you have a sodium here and a chlorine there. They don't come and stick together as a sodium and a chlorine, okay? They don't come apart and hold together like a compound does, like a molecular compound does, but they just come apart, and it's like, oh yeah, here's a sodium, okay? And then there's a chlorine over there, and they stay separated, but they're all in the water. They're just not connected in the water. And because they're not connected in the water, then each of those little ions, all those little chlorine ions, they're now negatively charged, and so they can move freely. The sodium ions can move freely in the water as the electrical charge is being put into the water. If I start to put a potential into the water, a voltage potential, then all of a sudden these things can move around. It's pretty cool. So anyway, this kind of gives you a summary of the different types of solids that we are talking about here in this section of our chapter. Okay, so let's go into a little bit more detail as far as what the actual electrons would look like if we were doing a transfer of electrons. Because remember, ionic compounds have transfers of electrons, and the covalent compounds have a sharing of electrons, okay? So you see that I've started both of them with the first energy level has 2 electrons. That's the first energy level. The second energy level can get to 4 electrons, right? So we can put 4 electrons in the second energy level. Sorry, did I say 4? 8 electrons. I was counting 4 more because I'd already had 4. 1, 2, 3, 4, 5, 6, 7, 8. So our second energy level can have 8 electrons. So we'll get 8 and there's 4. Count 4 more. Don't make my mistake by saying there's 4 again. All right, so 8 electrons in my second energy level. Now, remember, sodium has a total of 11 protons, right? And it has 11 electrons. Chlorine has 17 protons, and it's got 17 electrons. Okay, well, I've got some work to do here to fill in my rest of my electrons. I've got 10 so far. 2 plus 8 is 10, and I've got to get to 17, so I need to add 7 more. 1, 2, 3, 4, 5, 6, 7. Sodium just has 1 electron in its outermost energy level, right? 1 valence electron. And so now ionic bonds like to transfer their electrons. So what happens is sodium wants to have 8 in its final outside energy level, and chlorine wants to have 8. Well, sodium's got 1, chlorine's got 7, and so sodium wants to give its 1 over to chlorine. When it does that, now I've got 18 electrons for chlorine, which gives this whole thing a -1 charge. And now for my sodium, I now only have 10 electrons. And so that gives this thing a +1 charge. Okay, because it's got 11 protons, 10 electrons, 11 positives, 10 negatives. This one's got 17 positives and 18 negatives. And so this is going to have a -1 charge. So these are now going to be attracted to each other because one has a slightly positive charge and the other has a slightly negative charge. And this is what makes ionic compounds a little bit more attracted, a little bit stronger in bonding than covalent compounds, because they've transferred the electron and now they are opposite charges attracted, okay? And so yeah, that's our ionic compound. Let's talk about this with regard to a little diagram we have, or a little animation we have, I'm sorry. Now, this is kind of a fun way to look at it. Remember, the electrons aren't shared. We have charged particles, the opposite charges attract. I like this little illustration here because we've got 2 different dogs. They're both coming in with bones, right? Those bones are representing the electrons. And as these dogs come in, the big dog that wants electrons more, in this case, chlorine really is electron hungry. It's highly electronegative. It takes that electron away from sodium because sodium doesn't want it that badly. But once it is there, now the other dog kind of nuzzles up next to the dog that just took its bones, like, oh, okay, can I maybe have that someday? And the other dog's like, no, it's all mine. Okay, but these guys are all hanging out next to each other now because the electron transferred, and now one of them has a positive charge, one of them has a negative charge. Again, the reason that dog took it is because it wants electrons more. Chlorine wants electrons more than sodium, and so it pulls the electron so far and so hard toward itself that it actually basically rips it away from sodium, and so we call that the transfer of electrons. So that's ionic bonding. Okay, so where do we see this? It's kind of cool to look at what happens with ionic bonding. One of the things that you've maybe discovered or heard about at some point is that ionic compounds have cleavage lines, okay? That these crystals can be cut along particular lines. Maybe think about mica, okay? If you think about the mineral mica and how it can cleave and it has like these sheets or these layers that kind of peel off. Well, other elements can do that same kind of thing. Okay, not elements, sorry, other compounds can do that same kind of thing, where if you put pressure on one spot, then it breaks cleanly and evenly, okay, down those lines. As an example, I have a crystal here, and you can see that it's got so many of these unique like ridges and lines. Okay, these are all these fracture points, these little fracture lines that you have where it cleanly breaks in a particular cleavage line. And that is what we're talking about here when we show this little hammer beating down on a couple of these little ions here. So normally negatives and positives are next to each other, but if I can put a little pressure on the negatives and I can align those atoms momentarily to be negative upon negative right here, right, positive on positive, then all of a sudden these negatives are now repelling each other. And this is why things like these crystals can actually cleave upon particular lines, because when you put a little pressure on them, it aligns the like charges next to each other and they repel, and now it falls apart. Pretty cool, right? All right, so that's an example. Calcium fluoride is an example of a type of crystal, and this is something that you would see if you were looking at fluorescent, some types of fluorescent crystals are calcium fluoride. And then this is just sodium chloride, I think is what we're trying to show on this one. This is like sodiums, and that the sodium chloride could, cleave. This one, I believe, I'm gonna have to look this one up again. I'm pretty sure that crystal is, oh, I don't even want to say it. I'm so ashamed that I've forgotten what it is now. I'll tell you some other time. Okay, let's look at conductivity. Again, the idea here is if I have a solid, it's not going to be conductive. This is potassium iodide, and this is not going to conduct electricity if it's a solid, because those crystals can't move around. Those little charges, those little ions can't move around. But now once you put it and you melt it, this is some flame under here, now these these ions can move around, and so now this can conduct electricity. And if you put it in water, where now it's surrounded by water and they've come apart, then it can also conduct electricity. Let's talk about covalent bonds. Okay, in a covalent bond, we have the same thing here. Now we've got chlorine, but we've got chlorine twice. So remember, we had 1, 2 in the first energy level, 1, 2, 3, 4, 5, 6, 7, 8 in the second energy level. Let's do the same thing here. 1, 2 in the first energy level, 1, 2, 3, 4, 5, 6, 7, 8 in the second energy level. In the third energy level, remember, we have 7. 1, 2, 3, 4, 5, 6. I'm going to put one of them right here, 7. And then in this second energy level, we have 7 as well. 1, 2, 3, 4, 5, 6. I'm going to put this one right in here, 7. Now notice what's happening here. They each have 7 valence electrons, but because I put them in the spot where they share the space, then they share the electrons. So now each of them basically has 8 electrons. Okay, so we count 1, 2, 3, 4, 5, 6, 7, 8 on this valence shell. And if I count this valence shell, it's 1, 2, 3, 4, 5, 6, 7, 8. We get to count them for both of them. They count for both. Okay, now we have 2 different types of covalent bonds. So this is one type of sharing. This is very even because they both want electrons exactly the same. Chlorine is going to pull on chlorine in exactly the same manner. And so these have an equal sharing. If they have equal sharing, we call them nonpolar covalent. If they have unequal sharing and one of the atoms is more electronegative than the other, then they're going to pull unequally, and so we call it polar covalent. We're going to show you those different types of bonds here, some examples of those. We're going to use the dog illustration of the dog animation again. It's pretty fun. So here's our nonpolar covalent. These are 2 dogs exactly the same. Okay, so these 2 dogs are both bringing the bones to the party, and notice how they're both sharing equally. They both have their mouth on an equal amount of the bone there, right? So they come in, they're like, hey, I want a little bit more, I want a little bit more, and so now they both get to have a little bit more of the bone, and they're symmetrically shared. Now look at what happens for their electron density. This is a cloud of their electrons, and you can see how it's nice and even. They're sharing everything equally there. Now let's look at what it would look like if that was a polar covalent. That was nonpolar covalent, right? So let's look at polar covalent. Now we've got two different dogs. One of them wants the electrons more. Fluorine is really electron hungry. Hydrogen is not as electron hungry. And so when they come together, look, this dog has got his mouth way over the middle of that bone, and he's pulling those electrons or the bone toward himself. And this little dog just got a little nibble at the end. Well, that's what's happening here. This part of my atom, which in this case is my hydrogen, has got just a little bit of nibble of the electrons. It's got a little bit of the electron, but not much. Fluorine has got a big part of that electron. And so the electron cloud, the extra electron, goes toward fluorine. And that's why we use these symbols to say it's a partially negative and partially positive charge, okay? And again, we call those partial charges dipoles, okay? So that's the polar covalent bond. Pretty cool, right? All right, so let's go through and talk about our metallic bonds. Now, again, I want you to remember, in this case, here we've got some copper. I'm showing you the nuclei here, and all of this little blue space around the outside, those are the electrons of copper. And copper has just got tons of little electrons, and it just shares them freely. It's not like every single electron is attached to that one particular atom. The outside energy electrons of metals can share their electrons freely. And so their outside electrons are in what we call an electron sea. They're not fixed electrons, they're mobile electrons. And so now these little electrons can just zip from one place to the next. And so if I apply a potential voltage to one side, then that electron is going to be allowing the other electrons to just zip right through. It doesn't have to hold on to it. It's like, no, that's my electron. It's like, okay, phew, I've got another one. Now you can have that one. Okay, and that's basically the way that this metallic stuff works. And so this is why metals are such good conductors of electricity, why they can do things like be reflective, why they're malleable. All sorts of great properties about metals are all because they have these free mobile electrons. And that's one of the coolest things I think about metals. But they still are going to have high melting points, okay, because they still are forming these crystals. So you can see that there's a regular order here of the actual center of the atom. And so metals have a regular centered structure, and so they have a crystalline structure inside them that is pretty fixed, but the electrons are not so fixed, which is kind of wild. Because in other things, we have electrons being the thing that determines kind of their shape. But in this case, the electrons don't have that same type of dictation. Okay, so let's see what kind of bonding we have. Now, I want this to be one of those where you practice. Okay, so I want you to pause it and practice. And now we're back. I hope you've gone through and identified these as the different types of bonding that we have present. If we have two nonmetals, we have covalent. And because they're the same, this is non-polar, right? They are sharing equally. Why? Because they are the same element. Potassium and fluorine, this is a metal with a nonmetal. And so this is ionic. This is two metals, so this is metallic. And this is a metal with a nonmetal group. Okay, and nonmetal groups work the same as nonmetals. And so this is also ionic. So those are the types of bonding that are present in those particular elements. Did you get them right? I hope so. If not, maybe go back and watch some of that lecture again. Now, I've talked about these three different types of solids, but I haven't yet talked about the network covalent solids. So I really quickly want to touch on a network covalent solid, which is kind of an interesting exception to these. It's a covalent bond, so it's like this one, but it's actually really, really strong. And it actually becomes stronger than this one. And so we want to talk about that. And the illustration I want to bring up to you is this little guy, okay? This bad boy. Ooh, it's so cool. All right, now, this is a crystalline structure of diamond. And you'll notice that it's got those green things in between each one. But these green ones now are the electrons that are shared in a covalent bond. And because these covalent bonds are shared in every single direction, it actually becomes stronger than the ionic compounds, which is kind of interesting, right? Typically, a molecular solid is going to have weak attractions to each other, right? But a network covalent solid is going to have strong bonds, right? They are covalently bonded network, and that network makes them strong. It's like a team all held together. It really makes it strong. All right, our properties, again, typically low melting points for a molecular solid, but high melting points, diamond. Whoa, really high and really hard, really strong, right? Very hard and inflexible. They're not good conductors, though. Another good example of this would be silicon dioxide, which is sand or quartz, okay? Attractive forces, weak attractive forces, strong attractive forces. So network covalent solids are a little bit different. They have some unique properties, but it's pretty cool. Sugar is a great example, sucrose. Sugar forms crystals, right? You have sugar crystals, but those are hydrogen bonds that hold them together, and you can put the temperature up and it starts to, come apart. Pretty low temperatures, 185 degrees. So not super low, but not super high. Okay, so what I want you to do, this is another practice time. I want you to try to list in order of increasing melting point these different substances, okay? So the lowest melting point to the highest melting point, what would they be? Okay, so pause it and practice. And you're back, okay? I hope you did it. Make sure you're practicing it, testing whether you know what you're talking about. So my first one is going to be carbon dioxide. Welcome back. Then got a sticky clicker. Carbon dioxide is the weakest attraction. It's a gas at room temperature. Then water, liquid at room temperature. Then sugar, it's a covalent compound, so not as strong bonds, right? And then iron is a metal. And then salt is the ionic compound. And then sand, that network covalent crystal, okay? So that's the way it should be if you talk about the increasing order of strength between those actual bonds. And you determine that based upon their melting point. Sand is going to have the highest melting point, okay? And carbon dioxide is going to have the lowest melting point.